Chapter 7, Lesson 1, Chemical Formulas and Equations on page 190. On the left-hand side of page 190 is the What You'll Learn section, which is also our objectives for today. Today we'll determine whether or not a chemical reaction is occurring. We'll determine how to read and understand a balanced chemical equation. We will examine some reactions that release energy and others that absorb energy, and explain the law of conservation of mass. Let's get started. Physical or chemical change. You can smell a rotten egg and see the smoke from a campfire. Signs like these tell you that a chemical reaction is taking place. Other evidence might be less obvious, but clues are always present to announce that a reaction is underway. Matter can undergo two kinds of change, physical and or chemical. Physical change in a substance affects only physical properties such as size, shape, or whether it's a solid, liquid, or gas. For example, when water freezes, it's a physical state change from a liquid to a solid, but it's still water. There's no chemical reaction. In contrast, a chemical change produces a new substance that have properties different from those to the original substance. The rust on a bike's handlebars, for example, has properties different from those of the metal around it. Another example is the combination of two liquids that produce a precipitate, which is a solid and a liquid. The reaction of the silver nitrate and sodium chloride forms solid silver chloride and liquid sodium nitrate. A process that produces a chemical change is called a chemical reaction. To compare physical and chemical change, look at the newspaper shown in figure 1. If you fold it, you can change its size and shape, but it's still newspaper. Folding is a physical change. If you use it to start a fire, it'll burn. Burning is a chemical change because new substances result. How can you recognize a chemical change? Well, figure 2 shows what to look for. In figure 2, it's showing from your sight, smell, the observation that you're making, is there some type of chemical reaction or change that's happening that isn't able to actually be reversed? So you've got the lightning bug that is changing its color chemically. You've got somebody drinking sour milk. If something's spoiled and gone bad, you can't make it better and fresh again. If something's burning, you can't undo that chemical reaction. On to the next page. Page 192, Chemical Equations. To describe a chemical reaction, you must know which substances react and which substances are formed in the reaction. The substances that react are called the reactants. Reactants are the substances that exist before the reaction began. Substances that form as a result of the reaction are called the products. When you mix baking soda and vinegar, a vigorous chemical reaction occurs. The mixture bubbles and foams up inside the container, as you can see in figure 3. Baking soda and vinegar are common names for the reactants in this reaction, but they also have chemical names. Baking soda is the compound sodium hydrogen carbonate, often called sodium bicarbonate, and vinegar is a solution of acetic acid in water. What are the products? You saw bubbles foam and the reaction occurred, but is that enough for a description? Describing what happens. Bubbles tell you that a gas has been produced, but they don't tell you what kind of gas. Are bubbles of gas the only product, or do some atoms from other vinegar and baking soda form something else? What goes on in the chemical reaction that can be more than what you see with your own eyes? Chemists try to find out which reactants are used and which products are formed in chemical reactions. Then they can write it in the shorthand form called a chemical equation. Chemical equation tells chemists at a glance the reactants and products and proportions of these substances present. Some equations also tell the physical state of each substance. What does a chemical equation tell a chemist? It tells us what is the reactants and then what are the products that are the result of that reaction. And there's a couple different ways in which these things are described for chemists and scientists. Using words, names, and formulas. One way you can describe a chemical reaction is with an equation that uses words to name the reactants and products. The reactants are listed on the left side of the arrow, separate from each of these by a plus sign. The products are placed on the right side of the arrow, also separated by a plus sign. The arrow between the reactants and products represents the change that occurred during the chemical reaction. When reading the equation, the arrow is read as produces. You can begin to think of processes as chemical reactions, even if you do not know the names of all substances involved. Table 1 can help you begin to think like a chemist. It shows the word equations for chemical reactions you might see around your home. See how many other reactions you can find. Look for the signs you have learned that indicate a reaction might be taking place. Then try to write them in the form shown in the table. So in the example here, you've got charcoal and oxygen. That would be when you're cooking something over the grill. And in the chemical equation, it's described as producing ash, gas, and heat, and that heat is what's being used to cook your food. Iron, oxygen, and water. When something is breaking down and rusting, you might see that. That's how it's described, and it's written out in that word form. If you're trying to cook on the stove with a gas stove instead of charcoal, you've got gas, the kitchen range, and oxygen being mixed together, producing gas and heat, right? So when that reaction is taking place, that gas has been ignited and is flammable, you're not using that to cook. That's how it's being described in word form. Using chemical names. Many chemicals used around the home have common names. For example, acetic acid dissolved in water is called vinegar. Some chemicals such as baking soda have two common names, and also known as sodium bicarbonate. However, chemical names are usually used in a word equation instead of common names. In the baking soda or vinegar reaction, you already know the chemical names of the reactants, sodium hydrogen carbonate and acetic acid. The names of the products are sodium acetate, water, and carbon dioxide. The word equation for the reaction is as follows. Using formulas. The word equation for the reaction of a baking soda and vinegar is long. That's why chemists use chemical equations. You can convert a word equation into a chemical equation by substituting chemical formulas for the chemical names. For example, the chemical equation for the reaction between baking soda and vinegar can be written as CH3COOH, which is acetic acid, plus NaHCO3, sodium hydrogen carbonate or sodium bicarbonate, that's baking soda. It's producing sodium acetate, water, and carbon dioxide, and it's described with that chemical formula that tells us which atoms are present and how many they are present by those subscripts. Subscripts. When you look at a chemical formula, notice the small numbers written to the right of the atom. These numbers, called subscripts, tell you the number of atoms of each element in that compound. For example, the subscript 2 in CO2 means that each molecule of carbon dioxide has 2 oxygen atoms. If an atom has no subscript, it means that only one atom of the element is in the compound. So carbon dioxide has only one carbon atom. Conservation of mass. What happens to the atoms in the reaction when they are converted into products? According to the law of conservation of mass, the mass of the products must be the same as the mass of the reactants in the chemical reaction. This principle was first stated by French chemist Antoine Lavoisier, who is considered the first modern chemist. Lavoisier used logic and scientific method to study chemical reactions. He proved by his experience that nothing is lost or created in chemical reactions. If you want to see more of this, click the link to the video on our page. He showed the chemical reactions are much like mathematical equations. In math equations, the right and left sides of the equation are numerically equal. Chemical equations are similar, but it is the number and kind of atom that are equal on the two sides. Every atom that appears on the reactant side of the equation also appears on the product side, as shown in Figure 4. Atoms are never lost or created in a chemical reaction. However, they do change partners. When they change partners, there's a bit of mathematics that comes into this part of the science where you have to actually balance these equations to say, do they actually have the same amount of atoms on each side of the equation? Page 195. When you write the chemical equation for a reaction, you must observe the law of conservation of mass. Look back at Figure 4. It shows that when you count the number of carbon, hydrogen, oxygen, and sodium atoms on each side of the arrow in the equation, you find equal numbers of each kind of atom. This means the equation is balanced, and the law of conservation of mass is observed. Not all chemical equations are balanced so easily. For example, silver tarnishes, as in Figure 5, when it reacts with sulfur compounds in the air, such as hydrogen sulfide. The following unbalanced equation shows what happens when silver tarnishes. Count the atoms. Count the number of atoms of each type in the reactants and the products. The same number of hydrogen and sulfur atoms are on each side, but one silver atom is on the reactant side and 2 silver atoms are on the product side. This cannot be true. A chemical reaction cannot create a silver atom, so this equation does not represent the reaction correctly. Place a 2 in front of the reactant Ag, or silver, and check to see if each equation is balanced. Recount the number of atoms of each type. So if you've got 2Ag, that's 2 of those atoms. H2S, there's 2 hydrogens, 1 sulfur. There's 2 Ags in the product side, 1 S, and 2 hydrogens. It's now balanced. There are an equal number of silver atoms in the reactants and the products. When balancing chemical equations, numbers are placed before the formulas as you did for Ag. These are called coefficients. However, never change the subscript written on the right of the atom in a formula. Changing these numbers changes the identity of the compound. We'll spend the next 2 lessons following today's lesson learning how to actually go through this process of balancing chemical equations. Energy in chemical reactions. Often, energy is released or absorbed during a chemical reaction. The energy for welding torch in Figure 6 is released when hydrogen and oxygen combine to form water. Energy released. Where does this energy come from? To answer this question, think about the chemical bonds that break and form when atoms gain, lose, or share electrons. When such a reaction takes place, bonds break in the reactants and new bonds form in the products. In reactions that release energy, the products are more stable and their bonds have less energy than those of the reactants. The extra energy is then released in various forms, such as light, sound, and thermal energy. Energy absorbed. What happens when the reverse situation occurs? In reactions that absorb energy, the reactants and are more stable, and their bonds have less energy than those of the products. In this reaction, water and energy being taken apart into form hydrogen gas and oxygen gas. In this reaction, extra energy is needed to form the products. It can be supplied in the forms of electricity. This is a way in which you're actually separating water into its gaseous forms. Reactions can release or absorb several kinds of energy, including electricity, light, sound, and thermal energy. When thermal energy is gained or lost in a reaction, special terms are used. Endothermic means absorbed thermal energy. Exothermic reactions release thermal energy. The root word therm refers to heat, as it does in thermos in the bottle and the thermostat or thermometers. Energy released. Several types of reactions that release energy. Burning in an exothermic reaction in which a substance combines with oxygen to produce thermal energy along with light, carbon dioxide, and water. Again, something that is releasing energy is called exothermic. Something that is absorbing energy is called endothermic. Rapid release. Sometimes energy is released rapidly. Here's a couple examples of some of those endothermic and exothermic reactions. Energy can be released slowly or rapidly. Sometimes energy is released rapidly. For example, charcoal lighter fluid combines with oxygen and air and produces enough thermal energy to ignite a charcoal fire within a few minutes. Slow release. Other materials also combine with oxygen but release thermal energy so slowly that you cannot see or feel it happen. This is the case when iron combines with oxygen in the air to form rust. The slow release of thermal energy from a reaction also is used in heat packs that can keep your hands warm for several hours. Fast and slow release energy can be compared in figure 8. So energy can be released slowly or rapidly. Lighter fluid, boom, you get this big explosion. That's a fast release. A slow release is an example of something rusting over a long period of time. What about energy absorbing? Some chemical reactions and physical processes need to have thermal energy added before they can proceed. An example of an endothermic physical process that absorbs thermal energy is the cold pack shown in figure 9. The heavy plastic cold pack holds ammonium nitrate and water. The two substances are separated by a plastic divider. When you squeeze the bag, you break the divider so that the ammonium nitrate dissolves in the water. The dissolving process absorbs thermal energy, which must come from the surrounding environment, the surrounding air, or your skin after the place you place the energy. So once you break these things and they mix together, it sucks all the heat from around it and turns that into a really, really cold pack. Therefore, you place that on the injured your ankle or knee. It's shown in the picture here, the knee, that obviously will then cool down that muscle or cool down that joint, that tendon. That is going to allow that healing process to take place. But that's an example of an energy absorbed reaction. Energy in the equation on page 199. The word energy often is written in equations as either a reactant or a product. Energy written as reactants help you think of energy as a necessary ingredient for the reaction to take place. For example, electrical energy is needed to break up water into hydrogen and oxygen. It is important to know that energy must be added to make this reaction occur. Similarly, in the equation for an exothermic reaction, the word energy often is written along with the products. This tells you that energy is released. You include energy when writing the reaction that takes place between oxygen and methane and natural gas when you cook on a gas range, as shown in figure 10. This thermal energy cooks your food. So you have the example of methane and oxygen burning to form carbon dioxide and water. That's when you're cooking something right on the gas stovetop. Although it's not necessarily writing the word energy, can draw attention to an important aspect of the equation. Now hopefully you finished the first section of your note-taking worksheet, and your assignment is to complete the section 1 of the reinforcement. I want to talk you through some of those instructions. In numbers 1 through 4, it asks you to complete the following sentences by writing the correct terms in the blank. In numbers 5 through 10, it asks you the following questions on the lines provided. Number 5 says, give 2 reasons why scientists prefer to use chemical equations instead of word equations. It's having to do with why things are so long to write those things out and how it could be clearly communicated across different languages. Number 6, what do the subscripts in the chemical equation tell you about the equation? Remember, the subscript applies to the letter in front of it, telling you how many of those atoms there are. Number 7, suppose you have a holiday celebration and over the evening 6 logs are burned in a fireplace. All that's left is ashes, but you know that there are just as many atoms as there were before. They're just in a different form. Explain how you know that. It's our law of conservation of mass. Number 8, the fire in the fireplace is an example of an exothermic reaction. Explain what happens in an exothermic reaction. Remember, exothermic and endothermic, the difference between those two. Number 9, in one of the lab experiments you observed water was split into hydrogen and oxygen in an endothermic reaction. Explain what happens in an endothermic reaction. So number 9 is referring to the diagram on page 197, figure 7, where electrical energy is needed to break water into its components, and it's changing water into hydrogen gas and oxygen gas. Why is that considered an endothermic reaction? And number 10, it says if the equation below is balanced, write yes on the line provided. If it is not balanced, write no. Here you're being asked to count the number of atoms on both sides of the arrow, and if they have the same number of atoms on both sides of the arrow, then you would say yes. If they don't, you say no. Tomorrow we'll learn how to actually fix those equations that aren't balanced and balance those equations as we practice learning that skill. God's blessings. Thanks for following.